What if you actually fell into a black hole right now? Not as some thought experiment, not as a far-off sci-fi fantasy, but you, your body, your consciousness, just gone. Swallowed by the most violent, most mysterious object in the entire known universe. What would you see? What would you feel? Would you feel anything at all? And here's the part that's going to genuinely disturb you. Scientists actually disagree on whether you'd be torn to shreds instantly or whether you'd drift through peacefully without feeling a single thing. Two completely opposite fates. And the reason they disagree reveals something so deeply strange about reality that it will change the way you think about space, time, and your own existence forever. Let's start somewhere most people never think about. Right now, as you're watching this, there is a supermassive black hole sitting at the center of our own galaxy, the Milky Way. It's called Sagittarius A star, and it has the mass of 4 million suns crushed into a point so small it doesn't even have a real size. It's about 26,000 light years away from Earth. Safe. For now. But there are black holes scattered all across the universe, and some of them are wandering. Rogue black holes drifting silently through space with no star to orbit, completely invisible, detectable only if they happen to bend the light of something behind them. No warning. No glow. Just darkness eating darkness. Now before we actually fall in, you need to understand what a black hole really is, because most people picture it completely wrong. They imagine some kind of cosmic vacuum cleaner, sucking everything in. That's not what it is. A black hole isn't a thing that pulls. It's a place where gravity is so extreme that space-time itself bends beyond the point of return. Everything in the universe follows the curves of space-time, planets, light, time itself. Near a black hole, those curves become so steep, so sharp, so absolute that every possible path forward in space-time points inward. There is no direction that leads out. Not up, not sideways, nothing. The very geometry of space is broken. And the boundary where that happens, the point of no return, is called the event horizon. Cross it, and the laws of physics, as we understand them, stop making predictions you can trust. So here you are. You've somehow ended up in space near a stellar mass black hole. One formed from a collapsed star, maybe 20 or 30 times the mass of our sun. These are the smaller ones, and smaller, in the world of black holes, is extremely bad news for you. You're drifting toward it. What do you see? First, something absolutely extraordinary happens to the light around you. Because this object is bending space-time so severely, the light from stars behind the black hole wraps around it. You would see stars that are physically behind the black hole appear around its edges in a glowing ring. Stars that don't exist on that side of the sky suddenly appear. The entire background of the universe, every star, every galaxy behind it, compresses into a thin, luminous halo surrounding an absolute circle of darkness. Scientists call this a photon ring. It's one of the most beautiful things that physics predicts, and it's real. We've actually seen it. The first image of a black hole captured by the Event Horizon Telescope in 2019 showed exactly this, a glowing orange ring around a shadow. That shadow is not the black hole itself. It's the absence of everything. Light going in and never coming back. As you drift closer, something subtle begins. You notice the stars on the side of the sky facing the black hole are shifting, moving, clustering. This is gravitational lensing doing something to your entire field of vision. Space is acting like a lens. Then something else. On the far side, the stars start moving too, spreading apart. Your entire sky is warping around this gravitational monster. Now you're close enough that you should start to feel something. And here's where it gets uncomfortable. Gravity doesn't pull on you as one unit. It pulls harder on whatever part of you is closest to the source. Right now on Earth, the difference in gravity between your feet and your head is so tiny it means absolutely nothing. But near a black hole, particularly a stellar mass one, the difference in gravitational pull between your head and your feet becomes enormous. One side of your body is being pulled significantly harder than the other. And what happens when you pull something from both ends with dramatically different forces? It stretches. Physicists call this process spaghettification. Yes, that is the actual scientific term. Your body would be pulled into a long, thin strand of matter, atoms stripped, particles separated, drawn down into the singularity in a stream of what used to be you. You would not survive to reach the event horizon of a small black hole. The tidal forces would end you well before that. But wait, here's where things get philosophically insane. Because if instead of a stellar mass black hole, you happen to fall toward a supermassive black hole, something like the one at the center of the Milky Way, or the one at the center of the galaxy M87, which has the mass of 6.5 billion suns. The story changes completely. Completely. Because the event horizon of a supermassive black hole is so enormous, so impossibly large, that the difference in gravitational pull between your head and your feet at the moment you cross it is actually tiny. Gentle even. You would feel nothing unusual. No spaghettification. No warning alarm. No physical sensation telling you that you have just crossed the most significant boundary in the universe. You would drift through the event horizon of a supermassive black hole, and you would not know it happened. That is one of the most disturbing things in all of physics. The point of no return, the moment after which you can never escape, never send a signal home, never interact with the rest of the universe again. That moment is invisible to you. Undetectable. You just float through it on a Tuesday afternoon and keep going. Now things start to get stranger on the inside. As you fall deeper, something begins to happen with time. And this is real. This is not science fiction. Einstein's theory of general relativity tells us that gravity warps time. The stronger the gravity, the slower time moves for the person inside it compared to someone watching from far away. This has been tested on Earth. We've put atomic clocks on airplanes and satellites and measured the difference. The clocks at higher altitude, where gravity is weaker, tick faster. GPS satellites have to account for this, or your navigation would be wrong by miles within a day. Near a black hole, this effect becomes extreme beyond imagination. If someone were watching you fall from a safe distance, something deeply strange would happen from their perspective. As you approach the event horizon, you would appear to slow down. Your image would redshift, the light coming off you stretching to longer and longer wavelengths as it climbed out of that gravitational pit. You'd appear to move slower and slower, getting dimmer and dimmer, your image frozen and fading at the edge of the event horizon. The light from your last moment stretched across billions of years. To the outside observer, you never actually cross the horizon. You become a ghost impression on the edge of forever. But from your perspective, you crossed it in a normal amount of your own time and kept falling. Two completely different realities. Both of them are true simultaneously. This is not a paradox to be resolved. It's a feature of the universe that breaks every intuition we have about what it means for something to happen. So you're inside now, past the event horizon, falling. And here's what the mathematics says about what you'd see. Remember that photon ring you saw from outside? All that light wrapping around the black hole? Once you're inside, light from outside the universe is still coming in. You're falling toward the singularity, but light from the entire history of the universe, all of it, is also pouring in behind you. Some physicists suggest you might see something like a bright ring, a whole panorama of the outside universe compressed into a shrinking window above you. The future of the outside universe might be visible to you, stars living and dying, galaxies evolving, all in a fraction of your experienced time. Others dispute this. The math gets slippery. The honest answer is we don't know exactly what you'd see in there. Because here's the brutal truth. General relativity, the best theory of gravity we have, the one that has passed every single experimental test we've thrown at it, breaks down at the singularity. The equations spit out infinities. They produce answers that mean nothing. A singularity isn't a place. It's a statement that our physics has reached its limit. We do not have a working theory of quantum gravity yet, and without it, what happens inside a black hole at its deepest point is genuinely unknown. We can describe the approach. We can describe the horizon crossing. But the final destination, the singularity, is a wall our mathematics cannot see through. And now comes the thing that keeps physicists up at night. The information paradox. Here's the problem. Quantum mechanics, the physics of the very small, the physics that describes atoms and particles with extraordinary precision, says that information cannot be destroyed. Every particle in the universe carries information about its state. Burn a book and the information isn't gone. In principle, you could reconstruct the book from the exact state of every smoke particle, every ash fragment, every photon of light released. The information is scrambled, but it's there. Now Stephen Hawking, one of the greatest physicists who ever lived, showed in the 1970s that black holes aren't perfectly black. They actually emit a slow, faint radiation, now called Hawking radiation, through a quantum mechanical effect at the event horizon. Over an almost incomprehensible timescale, a black hole radiates away its mass and eventually evaporates completely. But the Hawking radiation appears to carry no information about what fell in. It's perfectly random. If you fell into the black hole and the black hole eventually evaporated, where did you go? Or did the information that made up you go? Did it just cease to exist? That would violate quantum mechanics. But if it came back out somehow, that would seem to violate general relativity's insistence that nothing can escape the event horizon. This is the black hole information paradox. It's not resolved. Hawking spent decades working on it. The brightest minds in theoretical physics are still working on it. Some recent work suggests the information does come out, encoded in the Hawking radiation in a deeply subtle way. Others are exploring whether black holes might leave behind what's called a remnant, a tiny, stable leftover object that contains all the information. Some physicists like Juan Meldacena have proposed that through something called holographic duality, the information on the surface of the event horizon encodes everything that falls in, like a two-dimensional shadow of a three-dimensional reality. These ideas are profound and strange, and none of them are settled. And then there's the firewall paradox. In 2012, a group of physicists, Almhiri, Marolf, Polchinski, and Sully, together called AMPS, dropped something genuinely alarming. They argued that if information really does escape from a black hole through Hawking radiation, then the event horizon can't be smooth and empty like general relativity predicts. The requirements of quantum mechanics would force the horizon to be surrounded by a wall of high-energy radiation, a firewall, that would instantly incinerate anything crossing it, which means you wouldn't drift peacefully through the event horizon of a supermassive black hole. You'd hit a wall of fire and end. General relativity says no firewall. Quantum mechanics may demand one. Both cannot be right. Our two greatest theories of physics, the ones that between them explain essentially everything we've ever measured, are in direct contradiction at the event horizon of a black hole. Something about our deepest understanding of reality is wrong. We just don't know it yet. But here's what makes this beautiful rather than just frightening. Every answer we don't have is a door. Black holes have already given us some of the most astonishing scientific discoveries in history. Einstein predicted gravitational waves, ripples in space-time itself, from his general relativity equations in 1916. For 100 years we couldn't detect them. Then in 2015, LIGO felt the space-time shudder from two black holes colliding 1.3 billion light-years away. The signal lasted a fraction of a second. The movement it caused in the detector was smaller than 1/10,000th the diameter of a proton. And we caught it. In 2019, we photographed a black hole's shadow for the first time, something that should have been impossible. In 2022, we photographed Sagittarius A*, the one at the center of our own galaxy. And every time we look deeper, reality gets stranger and more magnificent. You sitting here right now are made of atoms forged in stars that lived and died billions of years before our sun existed. The carbon in your body, the oxygen in your lungs, the iron in your blood, all of it was processed through stellar furnaces and scattered across the galaxy in explosions. Some of those stars may have collapsed into black holes. Part of the story of what you are involves these objects. Black holes are not alien. They are woven into the fabric of what made us possible. So if you did fall into one, if you somehow found yourself on that trajectory toward the most extreme environment the universe can create, you would be witnessing the place where human knowledge ends. You would be at the frontier, not just of space, but of understanding itself. The universe has spent 13.8 billion years building complexity, building stars, building planets, building brains capable of asking these questions. And at the edge of a black hole, all of that arrives at the wall it cannot yet see past. And that wall is an invitation. It's the universe saying, "You haven't figured me out yet. Keep going. We will. We always do." If this changed how you think about space, time, or what it means to understand the universe, share it with someone who needs their mind broken today. And subscribe because we go this deep every single time. Now I want to hear from you. If you could ask a black hole one question, one thing you desperately want to know about what happens inside, what would it be? Drop it in the comments. I read every single one.